This is the 0.8. This is another situation. You got the data like this big, and we still calculate still look at the density for this two distribution. So in this case, which is more likely to fit this data?
The no.
Yeah, the no, yes. So in this case, so we still calculate the p-value. Remember the p-value represented the area under the curve, the blue curve. The area under the blue curve, which is beyond your test statistic. So beyond your test statistic means like on the right-hand side, right? Under the blue curve. So this p-value will give you what number? Something like 0.4, right? So if you got a p-value equals to 0.4, which is way more than 0.05, this will show a strong support for the null hypothesis based on your data, based on your test statistic. Is that clear? So I hope, yeah, it is clear that we try to link the hypothesis testing we discussed before using this special case. So here we have two dresses, right? I'm gonna mention this again. So we only put the blue dress on ourselves to see if our data is, if our data fits this dress. If the p-value is big, which means, yeah, our data, our test statistic fits the blue dress very well, so we're gonna take it. Otherwise, if our data gives you a very small p-value, which means your test statistic does not fit the blue dress that well, so you're gonna reject that blue dress and take the orange one. Does that make sense? Okay, so in this case, suppose, now let's go back to Ryan's question. So what is the power here? So the power is like, given the drug is indeed effective, what is the chance you're gonna successfully reject the null hypothesis and claim this drug is an effective one? So that's the power. Okay. All right. Let's continue. Okay, then, so this is a simple example. I used the t-test. So here you see, so in this t-test example, so we have two t distribution, right? T1 and T2. So, okay, this is not related to our genetic testing, right? We are interested in, so let's go back to our business. So we are interested in testing whether the additive effects or the dominant effect is equal to 0 or not. So here we want to test the difference here, the reduction here value is whether this d value is equal to 0 or not. So this is our test, right? We use two distributions here. And here we want to test what? We want to test if B, let's say dominant, let's say the additive effects, if this thing is equal to 0 or not. So this is the statistic we're gonna use, right? So I hope you still remember. So here, this is the statistic we try to use. And this thing is a Watt statistic, which is chi-squarely distributed, okay? Is that clear? The same thing. So now we are testing whether B equals to 0 or not. So in the previous slides, we tested D, right? So here we test the B. So B is what? B is, for example, B is the additive effects. We want to see if additive effects is equal to 0 or not. This is how is this related to our biological question? So if B equals to 0 means, okay, this locus is non-relevant, is irrelevant to our phenotype, right? However, if B is not equal to 0, which indicates this locus is indeed contributing to the variability of the trait. Is that correct?
Got it.
Yes, okay, very good. So now we use the same thing. We constructed this statistic. And okay, now the null hypothesis is very clear, right? We want to test whether B equals to 0 or not. And the alternative dress here, although we don't put this dress on, but we're gonna use this as a alternative hypothesis. We're gonna test this only using the non-distribution. So if B equals to 0, this whole thing is following a central chi-square distribution, which is here, the first solid line. Okay, the solid line here. So if B equals to 0, then this test statistic is following a chi-square distribution, which has the center equals to I should say that. So if B equals to 0, the same, A equals to 0, additive effect equals to 0, then this whole thing, the test statistic, is gonna following a central chi-square distribution, which is the solid line in this graph. Okay. However, if B is not equal to 0, or the additive effect is not equal to 0, then the same thing is still following a chi-square distribution, but it is following a non-central chi-square distribution. For example, which is the dashed line here. So you're gonna see, you still see two dresses here, right? Two dresses here. So we're gonna only test our data based on the solid dress, not the dashed dress. Okay. So this is the H null distribution, and this is the H alternative. Okay, so the two distribution are both chi-square, but they have different centrality. Let me see. They have different the centrality. So am I right? Centrality, yeah, the centrality parameter. So if it is a central chi-square distribution, the centrality parameter equals to 0. However, if it is a non-central chi-square distribution, then we have another parameter here, theta, which is the non-centrality parameter. Okay. All right. So okay. So now we think about the previous slides. We compare two distributions here, right? So here we also compare two distributions. Suppose you got a value for this test statistic here. Okay, this is the value you summarized from your data. So suppose you got a value like this big, 23. What do you think? Do you think it fits the non-dress better or the alternative best dress, the dress better? So if
alternative.
you got it, I'm sorry?
I was going to say alternative.
Yes, very good. Because if you got a big value for your test statistic, it is a strong evidence against your null hypothesis, right? The p-value is very small. Is that correct? So however, if your data, if you calculated the test statistic from your data and the statistic appeared to be here, 5. What do you think? What do you think? Do you reject your null hypothesis or not?
Accept
No.
Yes, right. You're going to accept, right? Because if your null hypothesis is true, it is very likely you're going to see the data like this. The data will give you something like the test statistic equal to 5, right? But the chance, if the null hypothesis is true, the chance of getting a statistic as big as 23 is very low. So the 23 will make you reject the null hypothesis, but the 5 will make you accept the null hypothesis. Is that correct?
Mhm.
Okay, I hope I hope this is clear to you. So this is very interesting and important. So once you to understand what we are doing behind the hypothesis testing, so 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 in the future when you deal with the real biological problem, so it will be crystal clear for you to understand what is going on, what data you look at, and what is the hypothesis, what are the hypotheses you are comparing, and what the conclusion you can make from your test statistic. Okay. All right. Okay, so let's look at the relationship between the type 1 error and the type 2 error. So suppose this is the non-hypothesis, right? And of course, the second distribution is the alternative hypothesis. All right, we only test the H0, the non-hypothesis. And all right, suppose this is the critical value. The critical value we use to make to either so this is the critical value we use for either accepting the non-hypothesis or rejecting the non-hypothesis. All right, so if we set up this value, so usually this value is associated with alpha equals to alpha equals to 0.05. So this is the value we are very familiar with, right? So in most of the statistical test, we use alpha equals to 0.05. Suppose, so this distribution is a normal distribution. And so this area, so when we use the alpha equals to 0.05 means beyond this point, the area under the curve of the non-distribution equals to 0.05. Is that clear? And that alpha equals to 0.5 means type 1 error. So can anyone help me explain why we call this is an error, type 1 error? Can anyone help me to understand why we treat this red area, which is the area under the curve beyond the cutoff we use under the non-distribution, is the type 1 error?
Is it because of the size of the area?
Yes. And why we use this, I mean, yeah, this is the size, the 0.05. So why do we call this area as a type 1 error area? Because even the non-hypothesis is true. You still, yeah, it is possible, although it is not likely, but it is still possible that you end up with a test statistic in this area, right? So this is what I want to say. So even your non-hypothesis is true, it is still possible. Even it is not likely, but it is still possible for you to end up with a statistic in this area. Do you agree? Yeah, of course. This is the whole distribution, right? So majority of the times, so if you like carry it out 1,000 times of the test, so for the most of time, you're gonna end up with a statistic within this region, right? Because it is more likely you end up with a statistic in this region. But still, it is possible, although it is very unlikely for you, but it is still possible for you to end up with some statistic falling in this region. Is that correct?
Yes.
Yes, very good, very good. Okay, then what happened? So suppose you are not that lucky, so you just did one experiment. If, for example, if the null hypothesis is true, so this is the truth. So, but you are not that lucky, so you end up with a statistic in this area. So, what is your test conclusion? Please tell me. Given the null hypothesis is true, but your data will reject the null hypothesis, and you're gonna claim the alternative hypothesis is true, right?
Mhm.
So actually, this is wrong. This is an error. But what's the chance for this? The probability. That's the chance.
5%.
The area is the chance, right?
Yeah, 5%.
Yes. So this is why we call this is the type 1 error. Is that clear?
Yep.
Yes.
Okay. Now let's look at the yellow part. Yellow part is the type 2 error. So if you well understand the type 1 error, then it's very easy for us to understand type 2 error, right? So suppose this time the truth is like your alternative hypothesis is true, okay? But you are the same, you're not that lucky. You end up with a statistic in this region, the yellow region. But remember, even the null hypothesis, so even the alternative hypothesis is true, but you still, in this test, you still put H null on the trial, right? So if you want to test if H null is true or not, but you got a test statistic falling in this region, what is your conclusion? Given A is true, but your data still support your null hypothesis. Do you agree?
Yep.
Mm.
So what's the probability for that? That's this area.
Would that be type 2?
Oh, no.
Or is that still type 1?
No, that's type 2. Type 1 is here.
Yeah, okay, so that's type 2. Got it.
Yeah, that's type 2. Because you use this as a cutoff based on the non-distribution. Whenever you got a statistic lower than this, you're gonna accept the null hypothesis, right? But in this case, if the alternative hypothesis is true, you end up with this test statistic. So you're gonna make a call that H null makes sense. You're gonna accept an H null, but in reality, the H alternative is true. So this is an error, another error, type 2 error. So the probability for type 2 error is this. Is that correct? Any questions? Very good. Okay, so as you can see, so type 1 and type 2, alpha and beta, are inversely related. So for example, if this is the test, we use cutoff here, which is the alpha equal to 0.05 as a selection criteria. So this is type 1 error and this is type 2 error, right? But if we want to reduce the type 1 error, say we want to use alpha equals to 0.01, we truly reduce the type 1 error. But what's the consequence? Because this test share the same selection criteria, right? If we want to reduce the type 1 error simultaneously, at the same time, we're gonna increase the type 2 error. Is that right? If we reduce the type 1 error at the same time, we're gonna increase the type 2 error. Can you see the relationship between them?
Yep.
Okay,
Yep.
very good.
I have a question about the HA distribution.
Mm.
So normally H null and HA is the same, like the same model. If it's normal, so both of them is normal distribution.
Yes, that's right.
Okay.
Yeah.
So
So yeah.
because
yeah, this is it. Yeah. So I think, yeah, for most of the time, like maybe I cannot say that's always true, but for most of the time, as I see, so in most of the case, the H null and the H alternative, they are following
Same
the same type of distribution, but with different parameters.
parameters. Okay.
Yeah. However, yeah, maybe there's some, like, I haven't seen that before, but I can imagine probably, yeah, there are some situations that you can use two different types of distribution to form your H null and H alternative.
Okay.
Okay. So is that clear? So in this slide, so clearly you can see the type 1 error and the type 2 error are associated with each other. So inversely, right? So if you want to use a more stringent cutoff to reduce your type 1 error, however, there's a trade-off, there's a cost. So that cost is you increase your type 2 error. Okay. Just like the yin and yang. So that's associated. So if you want to increase yin, then you're going to reduce yang. So if you increase yang, then you're going to reduce the yin. So they are inversely related to each other. And basically, we want to test if whether the hand fits the glove, which glove is better fitting your hand, his hand, actually. Okay. All right. So, however, so there's a way for us to control for both errors. For example, this is the situation. Okay, so if this is the H null and this is the alternative distribution, if this is the design, so we understand if we want to reduce the type 1 error, we're going to increase the type 2 error. So is there any way that we can reduce both? Yes. So if we have a better design, then we can control for both errors. For example, the distance between the null hypothesis and the alternative hypothesis, the distance here, let's say distance, we call this distance as there's a statistical term called the effect size. So if we can have a better design with a larger effect, the effect size, then we can reduce both errors. For example, look at here. So if you have a better design, and in this design, the distance between the null hypothesis and the alternative hypothesis has been increased. So the two distribution will be removed from each other, right? And then this will reduce both the type 1 error and the type 2 error. Or if you cannot design your experiment with a larger effect size, but you can also improve your design by having more experimental samples. For example, for both hypotheses, if you let me see what happened. Any questions? No. Okay.
Just one quick one for clarification. D in this case describes what?
So for example, let's use the tumor and the normal as well. So that D could be like the different differentially expressed value between normal and the tumor for one gene. So if you for one gene, let's say there are two genes. Let's say gene 1 and gene 2. They are both differentially expressed between tumor and the normal, right? But gene 1, the difference between normal and a tumor is smaller. But gene 2, that gene showed a larger expression difference between normal and a tumor. So in this case, we can say, okay, the effective size for gene 2 is larger than the effective size for gene 1, then in that case, the gene 2 will give you larger statistical power for detection. Is that clear?
Mm-hmm.
Okay. All right, so suppose you cannot change the effect size between the non-distribution and the alternative distribution. We still can do so. We can increase what is here or chat. Oh, sorry, so sometimes I cannot clearly. Okay. All right. Very good. Thank you. All right. So if you cannot change the effect size, so you can include more experimental samples in here, right? So for example, for both group, if you increase the sample size, you're gonna reduce the variance, the standard error for each distribution. Then this is equivalent to pulling these two distributions apart. Then you're gonna reduce both type 1 error and the type 2 error. Is that clear? Okay.
Mm-hmm.
Very good. All right. So this slide just show you the relationship between the normal distribution, the normal random variable, and the chi-square distribution. I have already provided a link to you, right? I uploaded that link on the iLearn, and so that link will provide some knowledge, interesting knowledge. Sometimes it's not that easy, but yeah, when you read it, so you can understand the relationship between different types of distributions. And this is an example. So actually, the normal random variable is associated with the chi-square random variable. All right. And okay, so as I mentioned, when we test our, so when we are coming back to our business, we want to test what? We want to test if B equals to 0 or not, right? So now back to our business, we want to test if the genetic effects equals to 0 or not. We are comparing the non-distribution, which is the central chi-square distribution, the first one, which is the non-centrality parameter equals to 0, with another chi-square distribution where the non-centrality parameter is not equal to 0. For example, this green one. However, yeah. So if we want to compare the blue one with the dark green one, so these two distributions are too close to each other. So that means like the power will be low. So it's very hard for us to detect. If there is a difference, it's very difficult for us to tell the difference between these two distributions, right? However, if we want to compare, if we want to compare this one with this one is the non-hypothesis. This is the alternative hypothesis. So look at the difference between the blue curve and this blue curve. They're quite different, right? Which means, yeah, if you want to test this design, so you're gonna have very much reduced type 1 error and the type 2 error. However, if you want to compare the blue curve with the red curve, so yeah, it's very hard. So in that case, you need a large, extremely large sample size to help you to detect the distance, the difference, the genetic effect, if there is any. Is that clear? Okay. All right, let's let's spend like maybe 10 more minutes. All right, so this slide shows the non-distribution. All right, so this is a central chi-square distribution here, okay? And let's learn some like basic concepts. So we introduce some basic concepts here. So next time, so we can talk about how we use this for the calculation and how we can use this to help us to make the core for the hypothesis testing. All right. So the probability, the cumulative probability, we use P to represent the cumulative probability when the test statistic takes a value like this, okay? So for example, if your test statistic is this large and the p-value or the cumulative probability is equal to the area under the curve, this is non-distribution. We are only talk about the non-distribution, right? So the area under the curve of the non-distribution beyond this test statistic, this gives you the probability, the cumulative probability, or the p-value for the test. So this is a big name, right? So if you read value, if you read publications, papers, so you always see the p-value. So what does p-value mean? P-value means the area under the curve beyond the test statistic. You summarize it, that you summarized from your data. All right, that's the p-value. All right, and the cutoff here, we call this cutoff as a p percentile. So this value, the value, the test statistical value gives you the p-value equals to p is the percentile. That's the term you need to get used to. So we use this very frequently in statistical testing. All right, so this is for the central chi-square distribution, right? So let's talk about the non-central chi-square distribution. So for example, we have a distribution like this. This is the non-central, okay? All right, the same thing. For the central chi-square distribution I just mentioned, we have a non-centrality parameter, centrality parameter equals to 0. That's the central chi-square distribution, the non-distribution. And for the alternative distribution, so this value, this parameter is not equal to 0. It's something other than 0. And for example, this will push the distribution towards to the right. Okay, this is the alternative hypothesis. All right, so same, the p-value. So if we want to calculate the p, is still the same thing. And once we knew the p-value and we knew the degree of freedom and we also knew the non-centrality parameter, we can calculate the inverse function to calculate this cutoff value or the percentile. Or there's another version of the inverse function. So given the cutoff value, the percentile, given the degree of freedom and given the p-value, so we can calculate the value for the non-centrality parameter. So this is the new concept. So I don't think I have time to describe this in detail in class, either this time or next time. So I just introduced these concepts to you. Please, please read the textbook when you have time over the weekend. Or you can find some, let me see, chat. All right, okay, cool. So if you have time, please read. If you do not have time, please make some time. All right. So this is very important. I hope everyone will feel comfortable about this new concepts here. All right, so next time we're gonna talk about how we're gonna use this to help us to do some calculation related to power, because this is very important. This is another important topic in statistics, in experimental design. because in the future when you become a PI, if you want to write a proposal to get some money support from either NIH or NSF, so you need to show the plan, right? Experimental plan. So based on your facility or the money you apply for, so what's the required sample size you need to achieve this power? So you want to detect the genes that are differentially expressed between the tumor and the normal. So how many patient sample you need to get? So in this case, to answer this question, you need to know how to do the power calculation. So this is another major topic we're gonna learn next time. All right, I think today I'm gonna stop here. So any questions so far? Yeah, today we have learned a lot. Although so still don't worry, because we have like probably 20 something chapters in the book, but the major part is at the beginning. So we take time to learn the solid concepts. In the future, when we talk about the application, that's very quick, very easy. Once you feel comfortable with the basic knowledge, you will enjoy, you will appreciate the beauty of the application of this method. All right, any questions here?
Yeah, I have a question actually about the scale of the genotype indicator.
Yes, sure.
So about the example you showed us,
This?
yeah.
Mhm.
No, I think it's a previous slide.
Previous slides. Let me. Oops.
So
Not
the
here. No. Sorry.
no, it's things last lecture talk about the scale.
You mean this scale?
The scale of the genotype indicator. Yeah, this one.
Mm-hmm.
So I wonder, so how you for this example, because the original W we set the 0 for A1 and 0 for A2. So
They're not linearly related, right?
yeah, so I can find a CW to construct this.
Yes. Okay. So okay, sure. So okay. So let's see. So we how can I say that? Okay, let's say. So there's one way. The first way to define your Z and W. Okay. There's another way to define your ZW. So these two may not be linearly related to each other, but both of them, if they follow the rule to meet with the criteria for the F2 population, so both of them, either of them will work. So okay, so although these two kind of design are not linear related to each other, however, if you use this design, if you use like CZ times Z and CW times W, so this will gives you the same test with this one. Yeah, if you do the same thing here, this will give you the same test, and even this two can give you the same test results. Even you use different design, but these two are not necessarily be linearly related to each other. Yeah. So this is the beauty of this linear model, because sometimes you can choose your own design. So as long as they make biological sense, then yeah, you can use your own way to design the Z and the W random variable. Yeah.
Thank you.
Mm-hmm.
I still have confused. So you mean W makes sense from some point of view? Like
yes.
A1, A2, there is a D infection, but in A1, A1, there is a negative D.
So okay, so that's a good question. So let me explain. So in this case, as long as these two are independent, that's fine, right? So either you use like 1, 0, 1 for Z, or 0, oh, sorry, minus, right? Okay, you use 0, 1, 0 for W. This is another way, right? So we can show either way can gives you the covariance between Z and W equals to 0. So this makes sense. And since these two are independent, so as long as we can choose the way that show the biological meaningful relationship between the three genotypes, that's fine. Because yeah, clearly this is okay, right? Because the first genotype, so this shows the relationship between the additive effects, and this shows you the relationship between the dominant effect, right? The same thing like this. So first, using this way, you can also show the covariance between them is 0. That makes sense because the additive and the dominance are independent. And suppose you use, oops, give me a second. So if you use this way, so you just change the scale for A, right? Because yeah. But here the same. You just stretch the D, original D into this way because this is something like you times the original D by 2, right? Something like that.
So no matter which like if the covariance of Z and W is 0, no matter what number we choose, if the covariance is 0, then it makes sense, right?
Yeah, almost right. But we also need to make sure the way you chose for coding the W and the Z make biological sense. Because for example, let me think. So it's very hard to find a opposite example, the anti-example to show that. But so it is important that because you want to see the distance between these two in terms of Z are equal, right? And also the distance between these two should be equal. This makes sense in terms of the F2 population.
Okay.
Yes. Any other questions? All right, so this chapter is actually very important. That's why we try to keep a very slow but very stable pace to make sure everybody feel comfortable with this. This is so important. And as I mentioned, yeah, if there's something is not that clear to you for now, please, if you have time, take time reading the stuff online or the textbook. If you do not have time, please make some time. Yeah, and then next time when we talk about the chapter 7 and chapter 8, so yeah, that's really the difficult place. So we need to use these concepts. And after that, I think the same. The application is very similar for the future chapters. Let's see. Okay, so any other questions? Okay, if you do not have questions, let's stop here. And so this afternoon, we have a oh yes, it's office hours. Yeah, so if you have questions, please stop by. All right, bye bye. See you.
Bye.